Hello Science Alliance, hello IGCSEs, pretty much wiped the paint off my face. Welcome! So this is only our second IGCSE Physics lesson. We've got 2 years of IGCSE Physics spreading ahead of us. If you didn't see last week, it doesn't matter at all. This week we are looking at distance time graphs. So I gave you a question. I'm not going to tell you the answer yet. We're just going to go straight into graphs and I'll tell you the answer in a bit. I asked you if Usain Bolt, fastest man on the planet, fastest human on the planet, ran 100 meters in 10 seconds. How many meters did he run every second? Is it A, 1 meter per second, B, 10 meters per second, or C, can't say? I'm just going to let you stew on that for a little bit while we look at how you draw a graph. So all I'm going to do is I'm just going to draw a graph at you, and then I'm going to show you one that someone else has drawn, and it will contain 5 mistakes, and hopefully if you've been listening you'll be able to tell me what the mistakes are. So a graph is axes. This is just these lines here, okay? This is the axis, 1 axis, 2 axes pointing upwards. So and it's labelled Y. You don't have to label the axis, but when we talk about it, we call this one sticking up the Y axis. Y to the sky. And this one's the X axis, the one that goes across like that. So generally in IGCSE Physics, we're going to be talking about the Y and the X axis. I'm just going to shut my door, because I home educate my child, and it is not that child's time to learn about graphs. Right, so the next thing that you really have to do is to label your axes. What does this graph show? I've done myself a little distance time table here, so we'll just do that. Distance is going to go up the side here, so I'm going to label this distance. I can do it there, and you can still see it. There we go. And my distance, obviously it's really important. We were looking at units last week. Distance doesn't mean anything, does it? Was it inches, feet, furlongs, what? So this is meters. So I need to label my y-axis to say what that is and its distance and what the units are. Distance measured in meters. And this along here is going to be time, which it says here was measured in seconds. Now it's really important to fill your whole graph, right? So if my distance goes up to 6, I'm actually going to plot up to 12 at another point. So I need it to go up to 12. I wouldn't just kind of do 1, 2, 3, 4, 5 and stop at 12 there. We need to fill as much space as we possibly can so that we can read it the most clearly. So here goes, right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Nailed it. So this is 0 here. That's 0 on the y-axis and the x-axis. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And my time only goes up to 6, whichever one I'm using. So I'm going to really spread the time out. 1, 2, 3, 4, 5, 6. Here we go. And then I get to plot my points. 5, 1, 2, 3, 4, 5. Yeah, good. I'm not very good at typing and writing and talking. So if I was going to plot these on a graph, I mean, a lot of you will know this already, but I don't want to assume that anyone knows any maths in any of these IGCSE Physics lessons. So just very quickly, if I was going to plot these, then I would say, okay, let's say that it's someone running. So they've started at a 0 point. It could be anywhere. I've just decided that's the 0 point. And as they start running, I press my stopwatch. So at 0 seconds, they were 0 meters. So my first point would be there. After 2 seconds, they had run 2 meters. So I go along 2 seconds and I go up to where 2 meters is and I put another cross there. After 4 seconds, they had run 4 meters. Yeah, 4 seconds, 4 meters. You should draw graphs on squared paper. That's one of the things you should do. And after 6 seconds, they'd gone 6 meters. So there we go. So that would be my distance time graph for this data, and then I draw a line. Yeah, well, it's definitely better than yesterday. That's the main thing. Right, have I told you everything that you need to know to spot the 5 mistakes on this graph? Have I? I think I have. Yeah, I'm just going to give you it. If you've been to my website and you've got the worksheet, then you can actually draw on the worksheet what the mistakes are. But the people with the worksheets don't have anything that the people who are watching this lesson don't have. So you could just do it by looking at the screen. A foolish IGCSE student, what they're like, has drawn this graph, but they've made 5 mistakes. Can you spot them all? So you've got 2 axes, one that says meters, the y-axis says meters, and the x-axis says time. The y-axis is labelled 0, 1, 2, 3, 4, 5, 6, 7, and 1 square is one number. And the x-axis is labelled 0, 1, and then there's like a square gap, and it says 2, 3, 4, 5, 6. You've got 3 points on there, joined up in a straight line. The graph's taking up about a quarter of the graph paper available. Oh yeah, there's one thing actually that I didn't mention. So one mistake, you're going to have to work it out on your own. It's a really obvious one, but it's so obvious you might not get it. And try and be IGCSE about this as well, right? Because I know you can probably look at it and spot loads of mistakes, but can you also explain like why they are mistakes? Can you say in words what is wrong? That's actually quite hard. So I'm going to drink more water in order to not talk and let you think about it for a few minutes. Can you, because you're doing IGCSE, really, if you could write just a quick sentence saying why the mistake is a mistake, that would be great. Should we go through them? Have you got the really obvious one that I didn't mention? And I have made the same mistake, really. There's no title! So we have no idea what this graph is for. You've got to put a title on your graphs, dudes! This is something that all physics teachers and maths teachers are always yelling in classrooms. If there's no title on your graph, how can anyone know anything? The information is all completely useless, isn't it? There's no unit on the time. So this is kind of what I meant about using precise language. So meters is the unit, and what is time measured in? There's no use saying like, okay, that's 4, but what is it? Is it 4 seconds? Is it 4 minutes? Is it 4 hours? Let's say it's seconds and write that unit on in brackets. And the y-axis is the opposite, isn't it? We've got a unit, which is meters, but we don't know what it's not labelled, so it could be a height or a length, it could be a circumference or we don't know. So we'd have to put that on as well. And also, the scale absolutely has to be consistent. This is a weird one to get your head around, but you've really got to decide how many squares on your graph paper equals 1 or whatever, and then stick to it, because otherwise the graph, it's not correct. It's not reading correctly, right? Like you've said here that 1 square is 1 and 1 square is 1, but this square equals 2, but reading that graph, you wouldn't know that. So that would not be good. And finally, this is a sort of teacher gripe, but it does make it easier to see and do maths on if you need to do a gradient that we'll do later. There's too much wasted graph paper here. You've got to always fill it so your graph is as easy to read as possible. Why does this matter? Well, we did some all ages lessons a while back about weather and climate, and I found this graph and I thought, that's a really good example of why slightly tedious physicsy things like looking at units and titles on graphs can actually make a massive difference. Here is a real life graph. If you have ever, if you're unlucky like me and you spend a lot of time on social media, you might come across people who don't believe that climate change is real, who don't believe that humans producing a lot of carbon dioxide is heating up the world, right? Climate change. A lot of people who think that climate change isn't real will show things like this graph and say, ha, you see, this is proof. And actually, if you don't know a lot about graphs, it'd be really hard to understand why this was bad science. So here is a graph. It hasn't got a title, but it has got an axis. It's labelled, it says air temperature at the summit of the Greenland ice sheet. So at Greenland, they've measured the temperature of the air above the ice, and here's what they got. So the x-axis labelled years before now, so it's got 0 on the far right, and then it goes down to 11,000, all right? So this is like every 1,000 years it goes by. This is what the temperature of Earth has been doing. And people who don't believe in climate change would look at this and say, look, if you look at the big picture, then actually Earth's colder than it has been for ages. Earth's temperature is constantly changing. And look, people who think that the Earth's heating up, they're talking absolute nonsense. The reason why this graph is incredibly misleading is it is sort of relevant to the title. It's not a graph showing the temperature of the planet. It's just a graph showing the temperature of one place. So you can't use a graph showing the temperature of one place to prove anything about the temperature of the planet. And the other thing is this line actually stops in the year 1855. So most of the carbon dioxide given off by humans came about in the Industrial Revolution after this time. Can you see? I would never have spotted this, right? Without a lot of Googling. That's the year 0. They're saying that this is years before now. That's not quite right, because that's now, and the blue line stops just before it. Here is a graph which is showing what that graph said it was showing, if you know what I mean. Here is a graph where the axis goes all the way to pretty much the year now, and this red line shows how the temperature of the whole Earth has changed since 1850, which is a little bit more. But anyway, I just thought it's interesting to show that, graphs matter. If you've got the printouts from my website, you lucky things, you've got this in front of you. If you haven't, you'll just have to sketch this on a bit of paper. Can you please, thinking about how graphs tell stories, can you draw me a graph now to show how your happiness changes with the amount of donuts that you eat? So I'd like you to do an x-axis and a y-axis. The x-axis has donuts on it. I've put mine up to 12. And the y-axis has happiness on it. You can't put a number on happiness, can you? So I've just left that as, but let's just say that it starts at 0 and your happiness gets higher and higher and higher. Donuts goes along. Quick graph, please. How does your happiness change with the amount of donuts that you eat? I don't know what the units of happiness are either, so I'm not going to put those on. Have you done something? The reason why, if you've got the printouts, the reason I did it twice is because when I used to like doing this to my year 10s when I was teaching in a classroom. And what my year 10s would always do is, if I just flick you around to mine that I've drawn here, they would just go, oh yeah, easy, like that. And I just look at them like, really? Are you sure? So, like, you have 0 happiness whenever you're not eating a donut. That would be a very sad state of affairs, wouldn't it? Really, you're like as low as you can get whenever you don't have a donut. There's nothing else in the world that makes you happy. And then really just the more donuts you eat, the happier you are. Like up to infinity donut. No, dudes, try again. So just in case you were tempted to do that, I've given you this graph twice on the sheet. I'm going to fill mine in and then I'll show you and you can see how it compares to yours. Have you done it? Are you happy with your answer? I'll show you mine. It doesn't matter if you're still finishing off. So very quickly, I think I'm quite a happy person. So I've put my happiness to be sort of in the middle, but donuts definitely make me happy. I like donuts, which you would be able to tell from looking at this graph, right? So after 1 donut, I'm feeling much happier. After 2 donuts, I can't lie, I'm happier still. But I'm probably, the jump between 0 and 1 is bigger than the jump between 1 and 2. After 2, I'm still happier. After 3, regret is setting in. After 3 donuts, I'm still happier than when I just had 1 donut. I'm certainly happier than after I'd had 0 donuts, but it's starting to regret things. And after 4 donuts, I'm feeling less happy than I was originally. And after 5 donuts, I had to add in kind of minus happiness. So my donut graph goes like that, but it will completely depend on how much you like donuts. So someone would be able to read this graph and maybe get quite a good idea of how I felt towards donuts, how positive a person I was, how much I liked eating things. So there you go. Yeah, graphs tell stories. Let's go back to this question about Usain Bolt. So if Usain Bolt ran 100 metres in 10 seconds, because this is a distance time graph lesson, so we need to talk a little bit about distance and time. And if you know distance and time, you can work out speed. How many metres did Usain Bolt run every second? Well, you might have said 10 metres per second. And if you did, you were kind of intuitively calculating his speed, which is great. If you take the distance ran and you share it out among the seconds, you do get 10 metres for every second. So you could say that that was his speed, right? 10 metres per second. But is that really what happened? Like if we break the 100 metres that he ran into chunks of 10 metres, if you were just watching that 10 metre, would you see that he ran 10 metres in 1 second and then the next 10 metres in another second, the next 10 metres, another second? No, you wouldn't see that, would you? So what you've actually done there is you've worked out his average speed. We can't actually say how many metres he ran per second, like every second. But we can say his average speed for the 100 metres race was 10 metres per second. So if you look on the Edexcel specification, one of the people who might write your IGCSE Physics exam, you'll see that the equation, it says average speed is distance divided by time. So we're going to imagine that our objects today are going at a constant speed, right? They're not going to be, well, we'll look at different chunks where they do change, but we'll be looking at kind of a thing's average speed. Usain Bolt, FYI, actually was a bit faster than that. He ran the 100 metre race, it was 2009, in 9.58 seconds. So his actual average speed was distance divided by time, which is 100 metres divided by 9.58 seconds, which the average speed then, that all the newspapers were talking about after the race, was 10.44 metres per second. But in actual fact, that's not the exciting bit of the story, really. He actually ran faster than that. After he'd gone 52 metres, he was actually travelling at 12.32 metres per second. Over 12 metres in 1 second. The number that the papers gave was just his average speed. Right. Let's talk about how distance time graphs tell stories then. We will move on from happiness and donuts. So I said I had this little other table with some other data on. I'll do the red line this time. So this time let's say that I've timed someone else running. So I'm going to plot their numbers now. So when it was 0, the distance was also 0. So my red line is also going to go through 0. When it was 2 seconds had gone by, this person had run 4 metres. So 2 seconds, 4 metres. When 4 seconds had gone by, they had run 8 metres. So 4 seconds had gone by and they've run 8 metres. And when 6 seconds had gone by, they'd run 12 metres. There we go. So what's the difference? What can you see straight away? Why are graphs quite good? Why are graphs quite good for giving us quick, easy information? Well, the steepness of this line is called the gradient. And on a distance time graph, hopefully you can see here, the steeper the graph, the steeper the gradient, the faster that the thing is going, all right? So from looking at this point, you can see, okay, after 2 seconds, this blue guy had only run 2 metres, but after 2 seconds, this red guy had run 4 metres. So the red one's faster, but it's the gradient of that graph showing you that, yeah? So you could just look at a distance time graph and know straight away, if a line's looking like that, that's something going very fast. And if a line's going like that, then that is something going very slowly. So like 6 seconds has gone by, but it's still only gone a short distance. Is that all right? Okay, we will look at the maths of the gradient and how you put a number on the gradient in a sec. But first of all, I just want to check if you've got that, okay? So have a go at this sheet for me. Here we are. So you've got 5 distance time graphs here, A, B, C, D, and E. And I just want you to match the graph to the descriptions. So graph A is like a kind of averagely steep diagonal line, and then it flattens out. Graph B is a flat line, and then it's got a slightly lower gradient going up than A. C is a sort of average diagonal line, and then it's flat, and then it's the same slope of a diagonal line going off again. D, it's a fairly shallow line, and then that turns into a really steep line. And E, it goes up, and then it flattens out, and then it goes down again. So which one of those is you staying still for ages and then moving away at a constant speed? Which one of those is you moving at a constant speed and then stopping? Which one is you walking at a constant speed and then running at a constant speed? And which one would show you running at a constant speed and then stopping for a rest and then running on? So choose 4 for those ones, A, B, C, or D. And then question 2 is, which graph shows the fastest speed? What is happening in graph E, where it goes up and then down and then up and across and then down again? And question 4, for if you've finished. What are you doing? Why have you finished? Yeah, sketch a graph of your movements over the last hour, if you're confident in your answer to number 3. I might do that actually while you're working. I didn't do that yesterday. It's quite tricky, isn't it? That really gets you thinking, sketching your movements in the last hour. The last hour. Oh, okay. Yeah, I think that's right. Yeah. How are you getting on? Should we go through the answers? Have I gone too fast? Have I gone too slow? As usual, while I'm live on my Facebook page is a post at the top saying that there are no comments on YouTube, as you would have noticed, but you can comment on my Facebook post. So if you've got a Facebook account and you want to go to my Theatre of Science Facebook page, then you can comment on that post at the top and I will read it out at the end of the lesson and say hello to you. And if you want, you can say, "You're going too fast," or "I've been waiting ages for the answers, hurry up." And I'll get it later. Right, so you stay still for ages and then you move away at a constant speed. Which graph shows you staying still for ages? You need a graph where time is going by but no distance has been travelled. So that would be B, okay? You've got time going by but the number of the distance isn't changing. So that would be B, and then you start moving. Move at a constant speed and then stop. That's kind of the opposite. So that would be A. You're moving at a constant speed, time goes by, you move a certain distance, time goes by, you move that distance again, and then you get to a certain place and you just stop and time goes by, but the distance doesn't go up or down. You walk at a constant speed and then you run at a constant speed. So that would be D, okay? As time goes by, you going the same amount of distance each time, and then eventually the graph gets much steeper. So same amount of time goes by, but should we dig into this a bit? I'll tell you what, we'll do that when we look at who's running the fastest. And then if you run at a constant speed and then you stop for a rest and then you run on, that was C. You're moving, time goes by and you're moving, and then time goes by and you don't go any distance, and then you start moving again. Which graph shows the fastest speed? So that was D, all right? So let's have a look at this. Sorry, I didn't say, oh my goodness, how silly. Let's just imagine that all the squares represent the same amount, right? For ease, I'm going to say that each square is 1 second of time and each square is 1 metre of distance. So if we look at graph A, I can see here that for every second that goes by, this person travelled just a little bit over a metre, right? So if you count 1 second, you go 1 second into that first square, you go up, they travelled just a bit further than a metre. Graph B, when they were moving, 1 second went by and they'd moved less than a metre. And you could see that line's steeper, so we knew that anyway. So B, they were going quite slowly. D, when 1 second went by, they'd hardly gone anywhere. And then suddenly 1 second goes by and they've gone up 1, 2, 3 meters. So if you remember just, oh, the steepest line is the fastest, that's good. But also you could work it out right. 1 second goes by and they've gone 3 meters. So D was showing you the fastest speed. What's happening in graph E? Well, someone's going somewhere, stopping for a bit, and then going back to where they came from. So we'll look at the difference between distance and displacement later on, and how, like, if you're showing a sort of minus, yeah, we'll look at it later. But anyway, if you bothered to do your distance time graph of your movements over the last hour, oh, this one's mine. I think that's right. I'm going to say that my 0 point is me in my office. So I just sat teaching for ages and then started your lesson and had to leg it down my stairs, which I'm going to say they're about 12 metres away, to wash my face paint off. And then I sat in my downstairs toilet washing face paint off. And then I legged it back up the stairs to my 0 point, which is my office again. And I've just been sat here chatting to you. So there we go. That was interesting, wasn't it? Right. How to find... so I've said that this is the gradient, okay? How steep the line is. But just saying something's very steep or not very steep is not very precise, right? We're physicists, so we need to do something called finding a gradient. A lot of you will know how to find a gradient already. If you don't, I will link you to some stuff that helps you understand how to do gradients, but we'll just do it quickly. Because I said I'd always talk you through the maths, but I might just do it quite fast. So here's how you put a number on the gradient of a distance time graph. We're just going to keep pretending that 1 square is 1 second and 1 square is 1 meter, okay? So the first thing you've got to do is draw a line to find a distance off your graph, and it's better if the line is as long as possible, but it's also a good idea to find a point where the line crosses a square. So for example, I know that from here on my graph, this point here, all the way down to there is 1, 2, 3, 4, 5, 6, 7, 8 squares. If I was drawing my line here, like here, it'd be a bit trickier because it would be like 1, 2, 3, 4, and then a tiny bit squares, and that's a bit messy. So I'll go from here where it perfectly crosses a line. And you also need to find the corresponding... Wow, that's not right. Oh no, come here. I think my lines have got mixed up. Yeah, there we go. That one should go there. And that one should go there. I see. Talk amongst yourselves. Just with the lines and the appearing for understanding reasons. There we go. Great. Thanks. So we've got our line going down here, and we've got our matching line going across there. So wherever that line stops, you have to... I'm not explaining this well, but it'll all make sense in a bit. Wherever that line stops, you've got to measure back to the 0 point. So here we've got... Yeah, you go. I should have just showed you that. Measure a distance and measure the time that goes with it. So here we've got our distance from the top of the graph to the x-axis, which is 8 meters, 8 squares. And I can see that from there to the 0 point of the x-axis is 4 seconds. So our distance is 8 meters and our time is 4 seconds. And then you just divide the distance by the time. So the gradient of this graph is going to tell us the speed, because we know that it does. The steeper the gradient, the faster the speed. But this time we'll actually get a number for the speed. So you divide the distance that you've pulled out by the speed that you've pulled out, which in this case is 8 meters divided by 4 seconds, which is 2 meters per second, right? Or 2m/s, 2 meters per second. Now, you could have chosen any distance and any corresponding time from your graph. So for example, if I just... drew a line here, and then you can see that's 1, 2, 3 meters, and I've made my line stop there. So I could go across and say my line was like... it's not quite right, is it, actually? Sorry. 1, 2, 3, and then go across, and it's supposed to be 2, but it's not. So it's not... Oh no, that's right, isn't it? Yeah, that's pretty much right. So I was trying to show you that you can choose any distance and time, and you'll always come up with the same gradient. And of course, this is showing you that, because here I've pulled out 1, 2, 3 meters, and the time going across is pretty much 1.5. I've kind of drawn this out on PowerPoint, but it's about 1.5. So there you would do 3 divided by 1.5, which would still give you 2 meters per second. But that's a good illustration of why it's a good idea to try and find a line that crosses over. All right, I'm going to give you a couple of questions on that. If that was your very first time learning how to work out the gradient of graph, then I'm super sorry and best of luck to you. Have a go. It's good brain exercise. I'll give you the answers, and then, like I say, on my website where I post up the homework PDF, I will link you to some good websites that show you how to work out the gradient if you need a bit more time on this. But let's say that 1 square is 1 second and 1 square is 1 meter. I've given you the example of what I just did. Can you, if you've got the worksheet, it's a bit easier because you can draw the line, but can you sort of read these graphs and try and work out the gradients of these graphs? Work out the speed these objects were going when they were moving. But don't panic if you're thinking, what did she even just do? What does that mean? Then just try and find me any answer, and the going through the answers can be part of the teaching, can't it? You doing all right? We'll go through it because I'm worried that if you're not understanding it, it's a bit depressing just sitting here and not understanding. So let's have a look at A. All right, so I've chosen any line. I could have chosen that one, couldn't I? Which is a bit higher, but I've chosen this one. So how many squares is that? How many meters is that? 1, 2, 3, 4, 5, 6. And if I go across and find the corresponding seconds, then the amount of seconds are 1, 2, 3, 4, 5, 6. So if I'd gone up here, that would have just been 7 meters and 7 seconds, which would have given me the same answer. 6 meters divided by 6 seconds is 1 meter per second, okay? And is that okay? So you can see that if you'd started to find your gradient here and then gone across there, it would have been like 1 divided by 1, which would still be the same answer. With B, this is a much steeper one. So if I'm finding my line there, I've got a distance of 6 meters there, 6 squares, but this time it's only getting divided by 2 meters. So that one was going faster, which we'd expect because it's a steeper gradient. So that thing was going at 3 meters per second. And underneath here, well, you can find a gradient for both of these. The first one is 3 meters divided by 2 seconds, which is 1.5 meters per second. And the second one is also 3 meters divided by 2 seconds. So you can see it was going at the same speed as it went somewhere and then came back. But yes, we'll look at more of that next week. Right, are you ready for... This is what teachers call a plenary. It's supposed to be a kind of like fun activity to check your understanding at the end of the lesson. And so that I can see your answers and check whether I have taught it correctly or not. But this is actually a completely rock solid plenary. But I'm not sorry, I'm going to just... You've got to really keep your eyes out. One of these graphs is not all that it seems, okay? Study the graphs. One of the graphs is not all it seems. There has been a bank robbery. By the way, if you brought a piece of paper and some paper clips and scissors, keep hold of those. I'll tell you what I want you to do with those in the end. There's been a bank robbery. Police can't afford cameras anymore, but a keen physicist, fortunately, sketched distance time graphs of 7 people that were in the area when the bank robbery took place. Can you please match the names to the movement descriptions and find the guilty people? So again, if you've got my printout, you can sort of tick people off as we go, or you'll just have to do it in your head. Okay, so here's the distance time graphs of Olivia, Joseph, Ian, Ayan, Yusuf, Adiba and Chaz's movements. Study them carefully. One graph is not all it seems. Who, please, was waiting for a bus and they got on the bus? Okay, this person was waiting for a bus and then got on the bus. Who was waiting for a bus and then got on a bus? If you're feeling advanced and you know this straight away, can you tell me why I've made a mistake here? Why this is weird, not what happened? But which one am I thinking is the person who was waiting for a bus and then got on the bus? I'm only going to give you the answers at the end. Okay, so let's move on. This person was jogging, not walking. There is a walker and there's a jogger. This person was jogging past the bank at a constant speed. So someone's walking, someone's jogging. This person is jogging. Yeah, these are horribly done, actually. This is so awful, but I'm going to press on. This person, I will go through these again before the answers. This person ran out of the bank with the cash and jumped into a moving car. So one person has stayed still for a while and then got on a bus. One person has jogged past the bank, so they were both innocent. This person is not innocent. They ran out of the bank with the cash and jumped into a moving car. Who was that? Okay, I'm going to move on. This person was walking slowly past the bank. So I said there was a walker and a jogger. This person was walking slowly past the bank, so they are innocent as well. In fact, the walker and the jogger are innocent, so if you've spotted both of them, that's fine. All right, moving on. Did you spot that Yusuf's axes are a little bit twisted? What does that mean? This person hid in a cupboard in the bank when the police arrived and then snuck back into the safe. So they went into the bank. Well, they hid in a cupboard in the bank. And then they snuck back afterwards. You got them? So they're guilty as well. And this person flew overhead in a helicopter telling their fellow criminals when it was safe to enter and leave the bank. So this person is definitely guilty. There are 3 guilty people. Someone flew overhead in a helicopter. I should have said flew very fast. Helicopters can literally hover, can't they? Like the thing about a helicopter is that it can stay still in the air. But it wasn't. It was moving really fast. It was moving really fast. And finally, this overexcited police officer raced into the bank and fell over. Which overexcited police officer raced into the bank and then fell over? Just lay sprawled on the ground for the whole rest of the time. You ready to go through the answers? Was that the most annoying plenary that any teacher has ever created? I think so, maybe. So who was waiting for the bus and then got on the bus? And what mistake did I make? Why is it sort of weird? Olivia is innocent. Olivia was waiting for the bus and then got on the bus. But that's not how buses work, is it? This thing's moving at a constant speed. Every second that goes by, it's moving, what, like, let's say half a metre. Another second goes by, it moves another half a metre. Anything with a straight line gradient like that is moving at a constant speed. And that's not how buses work. It would have started slowly and then it would have got faster. But we will look at acceleration next week. This person was jogging past the bank at a constant speed. That was Ayan. So Ayan is completely innocent, just jogging past. This person ran out of the bank with the cash and jumped into a moving car. That must be Adiba, right? Only Adiba started off fast and then got faster. So Adiba is definitely guilty. This person was walking slowly past the bank, but it can't be Yusuf. It isn't Yusuf because Yusuf's axes are all mixed up. So Ian's going slowly, okay? Time is going by and he's hardly going any distance. So loads of time goes by, but Ian still hasn't moved that much. So Ian is walking at a snail's pace, but he's still innocent. It's Yusuf who's the weird one. This person hid in a cupboard and then they snuck back. That must be Chaz because they've sort of moved back to the place where they were before. And this person flew over in a helicopter. That was Yusuf, because Yusuf is in fact going incredibly fast. Can you see that? So hardly any time has gone by, but Yusuf has moved an enormous distance. So Yusuf is going really, really, really fast. So they were also guilty. And Joseph was the overexcited police officer who ran very quickly into the bank and then just fell over and didn't do anything. So if you made loads of mistakes there, definitely says more about me than it does about you. And I'm very sorry. Right, I'm going to flip you around. Hello, Science Alliance. Right, so there is something called, that is the end of our lesson, but there is something called a core practical that goes along with this kind of distance time graph measuring speed topic. It's not a practical that you actually have to do. You're not going to like do anything and an examiner isn't going to be like watching how you do it, but you do have to know about it. You have to know how it works, because you might get asked questions about it. And here is the incredible Save My Exams website with a beautiful summary of it. You can sign up, you can pay them to get access to more, but you can just see this without paying them. So yeah, they've got this core practical, which is investigating motion. And it's just basically timing something that is falling. They've suggested using a paper cone, but I think you should use a little helicopter instead, which I'm going to show you how to make now. So if you get a piece, obviously you have to do it right now, but if you get a piece of A4 paper and you cut it up the side, make a kind of, I don't know if a bookmark is really a measurement, but make a sort of wide bookmark shaped bit of paper and then cut a slit so it's got legs, right? It's like a wide bookmark with legs. Yeah, you get me. You done that? So what you should do is have like a meter ruler and mark the measurements, say off the side of a wall, stand on a chair if it is safe to do so, hold your thing like your paper cone or your helicopter, I'm just chatting while you get that done, and then drop it, or I suppose get someone else to drop it, and then have someone time how long it takes to fall to the ground, okay? And have it, and drop it after, like, you could say you drop it at 0.5 metre, and then you drop it at 1 metre, and then you drop it at 1.5 metres, etc., and you draw a table, which I'll show you, and you write down your results. You don't actually, like, you're not actually giving these numbers to NASA. They're not going to use it to like try and get people to the moon or anything. So if you don't have a meter ruler, it really doesn't matter, right? Just measure as high as you're comfortable measuring, call that 2 meters, and then the most important thing is that you chop the distance into even bits. So you could just say, oh, I'm going to say that's 4 meters, and in the middle of that point and the floor is 2 meters, and then the middle of that point and the floor is 1 meter. Do you know what I mean? It doesn't really matter. The most important thing is that you're drawing a table of results. Right, so when you've done that, fold the legs onto either side of the bit of paper, so you get this kind of little helicopter shape, yeah? And then you're just going to have to weigh down that helicopter with, I said to bring paper clips. I am using a blob of blue tack because I couldn't find any paper clips. But if you put on just the right amount of paper clips, just do a bit of experimentation, you should end up with a helicopter which falls, a bit worried that I've put on too much blue tack, it's going to plummet. But hopefully it will fall reasonably nicely. It's good, isn't it? You see that? Spoons! Yeah, and then the fabulous Save My Exams have suggested the table that you might draw, okay? I just thought we'll go through it because it looks a bit confusing. So they've done their distance as 1 meter, 1.2, 1.4, 1.6. That's up to you. So you just basically do the experiment once, hold your paper helicopter or whatever you've made, 1 meter, and then a bit higher, then a bit higher and a bit higher, and write down how long it takes to hit the ground. But then you do it again and again for reasons that we discussed last week, because you want to find an average time. So drop it 1 meter and time it 3 times. It might be like 1.1 seconds and 0.9 seconds and 1 second. So the average time, you would add all those up and divide them by 3 and get the average time. So when you're plotting your graph, you're only using the average time. It's a bit weird, isn't it? Like, you got all these times. You might think you need to draw 3 graphs, but no, you're finding an average time because that just makes your results more reliable. Like, say, the first time, I don't know, the sun was in your eyes, so you were squinting, so you get a ridiculously big or small time. You'd be able to see that because you timed it 2 other times. Does that make sense? I've said the word time a lot, but hopefully you get that. So do time 1, time 2, time 3, add them up, divide them by 3, and that gives you the average time. And then you would plot the average time on your x-axis and your distance on your y-axis and see what happens, yeah? But they've got a lovely description of it here. And they even talk about errors, which we talked about last week. So I'll link you to that. I'll link you to that in your homework PDF, but if you want to go to Save My Exams Core Practical Investigating Motion right now that you're all excited about it, then you can do it right now. And I think that's really the only way to properly understand the core practical. Because like I say, you won't have to do it for your exam, but they might well say, like, Susie has drawn this table of results. Where have they gone wrong? And if you've actually done it yourself, you'll be much more tuned into how it all works. Right, I'm going to go. That is the end of the lesson. Thank you so much, people who are supporting me. If you're not supporting me, then you can pay me for this lesson. How it works is most people who watch these lessons send me a £5 a month. So if you go to my About section on YouTube, which is where you are, if you go to the About section, you find this website called Coffee, and you can sign up to support me with £5 a month, which funds these lessons, because there's enough of you watching that £5 a month is enough added up that it's a job for me. But also, hopefully, £5 a month isn't that much for what you're getting. And I'll send you Theatre of Science magazine. It's very good. It's very unreliable. It comes out when I've written it. But it's very good. The latest one is on acids, which is, the magazine is great, and you will get it when you sign up. You'll get some free little sweets and some litmus papers, but you'll also get some diffraction glasses, which would be not unhelpful when you're studying IGCSE Physics. They're just like, well, they diffract white light so that you see rainbows. They're very cool, and I'll send you a description of how they work, which is pretty much about IGCSE level. Whoa, hello, Bastian, what's that? Oh, great! Bastian's movement graph looks a lot like yours. We were watching your Lego show. Oh, nice, yeah. Oh, that's so cool. That's your movement, distance time graph for your movements in between my Lego story show about glass. And now, that's really good. Oh, yeah, brilliant. Oh, I like that you've plotted the points really neatly. Oh, yeah, so I can totally see from that. That's very good. Anyone spot any mistakes in Bastian's graph? I think that's fine. Yeah, lovely. So is that distance up there? So that's meters. So you've gone about you had a little walk about 3 meters away, if that's where you were watching the Lego story show. I can see that Bastian, look, can you see that gradient's quite steep? So I'm thinking Bastian legged it about 3 meters away after the end of the Lego story show, and then slowly walked back to watch IGCSE. And I can see how much of a fidgeter Bastian is as well. Not much of a fidgeter, because you've just been sat perfectly still, not moving a centimetre away from where you are for 30 minutes. Ah, very nice. Interesting. Right, let's see who else has commented. No. Oh, Bastian. Hello, Bastian. Oh, Harriet's here. Hello, Harriet. Good to not see you. That's creepy, but you know what I mean. Hello, Amelia and Kitty. And here's Chloe. And here's John. Sorry, John. Hello. Thank you for coming, you lot. I'll just do a quick refresh. I think that's everybody, but I know it's always really annoying if you've just found out that I chat to you via Facebook and then I leave. Yep, so that's it. I'll see you next week when we will be doing speed time graphs. And like I say, looking at acceleration and lines that are curved, etc. No, I think that's it. Good. No one else has commented. All right. Thank you so much for coming, and thank you for supporting me. And Bastian, thank you for your little bit of paper, which is still hiding there. You've been coming for ages, haven't you? All right. I'll see you all next week. Bye.